In this video, we're going to be talking about improper integrals. In this chapter, we've been focused on different methods of integration, techniques that let us solve particular types of integrals. We've looked at integration by parts, trig integrals, trig substitution, partial fraction decomposition, and in the last section, or the previous section, we looked at integral tables and computer algebra systems. We also took a look at numerical integration, which is what we do when there's no antiderivative that's known. In this particular integral, we're going to be looking at integration again, but this isn't, well, it is an integration technique, but it's not focused on the integrand that being the problem. Instead, it's mostly focused on the fact that it is improper in some way. Now, what do we mean by improper? So this isn't exactly like the integration by parts or trig integrals or trig substitution, in that those were patterns that could be applied to certain types of integrands. These integrands could be completely and utterly different, but instead it's something about the structure of the integral itself that isn't proper. Now, there are two basic types. And one of the types has to do with integrating over an infinite interval. In other words, one of the limits of integration is infinity or negative infinity. So instead of integrating from, say, 1 to 5, we're integrating from, say, 1 to infinity, or even from negative infinity to positive infinity. So over the entire range of the x-axis. Well, that's improper, because infinity and negative infinity are not numbers, they're directions. So that makes the integral itself improper by having a limit of integration, which is a direction and not a number. There's another type of integrand that causes a problem and makes the integral itself improper. And that is when you have an integral over a closed interval that contains an infinite discontinuity. Now, let me say that again. You're integrating over a closed interval, so say 1 to 5, and it contains an infinite discontinuity. What does that mean? It has a vertical asymptote between 1 and 5. Well, that's a problem, because then the graph, of course, is shooting off to infinity or negative infinity and creating an infinite amount of space between the curve and the x-axis. And that can be a problem, of course, that makes it improper, because we have that infinite discontinuity between the lower and upper limit of integration. We have a value where that function does not exist. The only way to have an infinite asymptote in the middle, an infinite discontinuity, is to have 0 in the denominator. So buried between the lower and upper limit of integration, we've got a point where the function, the integrand itself, does not exist, and this makes the integrand improper. So we're going to be taking a look at how we deal with these. So it is a sort of an integration technique, but it's not focused on patterns in the integrand. Instead, it's focused on two different types. One, integrating over infinite integrals, where the limits of integration, one or both, are improper, infinity or negative infinity. Those are relatively easy to identify because you can see the infinity. The second type is much more difficult to identify. This is when you're integrating over an interval, and in that interval is a value that causes the integrand to be undefined. In other words, you have an infinite discontinuity, something that causes the denominator to be 0 inside that interval over which you're integrating. Now, it is possible to combine both these types together. So you could have an integral going over an infinite interval, so say between negative infinity and 5, but also have something that is undefined when x equals 3. So you've got two problems. You've got the lower limit of integration being negative infinity, which is not proper. It's not a number, it's a direction. And you also have a problem because the interval itself goes from negative infinity to 5, but it's not defined at 3. So you've got this infinite discontinuity in the middle of your interval. That one is more difficult to find. So let's now break it down and talk about how we're going to deal with these two different types of improper integral. I'll share my screen with you so that you can more easily see what I'm looking at. Now let's take a look at what we have. We're going to start with the first type, the more easily identified type, which is type 1, integrals over infinite intervals. Now, is it possible to have a finite amount of area in an infinite space? And the answer to this is yes, it is possible to do this, provided that the space, the infinite space, is diminishing fast enough, getting smaller and smaller as x approaches infinity. So what on earth am I talking about here? Well, what we're talking about might be something where we have an integral from, say, 1 to infinity of the graph of 1 over x squared dx. And we're trying to evaluate whether or not this exists. Well, it's improper because I've got a limit of integration, which is not a number, it's a direction. This is infinity, so this is a type 1. And I've got an integrand here, 1 over x squared. Normally, I'd have to worry about that, right? Because x better not be 0 or it's undefined. But notice that 0 is not inside my interval of integration. It's not between 1 and infinity. That would have made it a type 2. Now, if the integral had been between -5 and infinity, I'd have both types of problems. But on this one, the question is, if I look at this, and I'm looking at the graph of 1 over x squared, what does it look like? So when we graph 1 over x squared, we basically have something that looks like this. And the question is, if I go from 1 out to infinity, the graph itself never actually gets down to the x-axis. As x gets larger and larger, this expression, of course, gets smaller and smaller. So what I'm really talking about trying to find is the area under the curve. And I'm thinking that's going to be too wide for me to color. Let me get a little smaller. I'm looking to find this area right here. But in essence, that's an infinite space. You see that? That's an infinite space because this curve never touches the x-axis. There's always some space there. It's getting smaller and smaller, but there's space. Well, the question is, even though the space itself is in some sense infinite or an infinite region, does it have a finite amount of area? In other words, could I paint that infinite space with a finite amount of paint? Like go to Home Depot and buy 2 gallons, and I know the 2 gallons will completely cover that region, even though I can never be finished painting it because it goes forever. I know this sounds crazy, but the answer is yes, I can. Because in fact, this particular one is something that exists. So what do we mean by diminishing fast enough? Well, notice that this area that's between the curve and the x-axis is getting lower and lower and smaller and smaller. Now, it has to get lower and lower and smaller fast enough in order for this to be finite, to add up to a finite number. And again, we can think of this as some kind of Riemann sum on steroids, since it's going out to infinity. So we need to make more precise what we mean by diminishing fast enough. I mean, fast enough is not really mathematically precise, is it? So we need to figure out what does that mean and how can I precisely evaluate this by approximating it with something like a Riemann sum. Because again, this is a definite integral, except that it's improper because of the infinity. So here are the basic techniques that we want to follow in a case like this, where one or both of our limits of integration are improper. And again, the only 2 improper values they can have are negative infinity or infinity. That's either far left or far right. I mean, that's pretty much your choice. So here's what we're going to do. If one or both of the limits of integration are infinity or negative infinity, then we're going to replace that improper value, infinity or negative infinity, with a dummy variable. Now, a dummy variable means it doesn't matter what you call it. If you want to call it Tom, go for it. If it's going to be a mod, all for it. It can be a happy face. It's a dummy variable, and then it's going to show up in the middle of the integration. But by the time we evaluate it at the end, it's going to disappear. So it's an interim variable. It shows up in the middle, and then by the end, it's gone. It's not there at the beginning. It's not there at the end. It's only there in the middle part to help us evaluate. Typically, what we use is C and D. Now, why C and D? Because we use limits of integration from A to B. So they're reserving A and B for the limits of integration themselves. We're going to place a limit, back to calculus 1, a limit on the outside of the integral with the dummy variable, the one that we just replaced infinity or negative infinity with, approaching that form of infinity. So let's say that we're taking a look again at this integral that I had just a minute ago. And we need to go back to blue. The integral from 1 to infinity of 1 over x squared dx. Well, the first thing I want to do is I want to rewrite this as a limit. I'm going to replace infinity with c, and I'm going to evaluate the integral from 1 to c of 1 over x squared dx. So I'm replacing the improper limit of integration with a dummy variable, whatever you want to call it, and then I take the limit of the integral as that dummy variable approaches the particular improper value that I replaced it with. So this is how we're going to evaluate these. Now, I've replaced it, but I haven't actually done the integration. What order do I need to do these in? You have to evaluate the definite integral with the dummy variable in it first. C is considered to be a known constant, a real value, not in fact infinity. You're going to take the limit as c goes to infinity, but the c itself is considered to be a real value. Now, this makes it possible for me to evaluate the integral from 1 to c of 1 over x squared dx using any of the techniques of integration I've already learned. Integration by parts, trig integral, trig substitution, partial fraction decomposition, U substitution. How about just the power rule for integration? Anything I want to use to integrate. Then I have to plug in the limits of integration. Remember that we do that. That's the fundamental theorem of calculus. We plug in the limits of integration, and we subtract the value with the upper limit plugged in minus the value with the lower limit plugged in. After I get a result, I've completely evaluated the definite integral, right? Found the antiderivative, substitute the upper limit of integration, substitute the lower limit of integration, subtract the lower limit of integration substituted in from the upper limit of integration substituted in. Get some expression. Now, this expression is going to have c in it, isn't it? Right? It's not going to disappear. It's still going to have c in it because c, while it represents a finite real number, I haven't specified what it is. So it's still going to have c in it. And then when I'm completely done with that integral, then I take the limit of what's left with c approaching infinity. If that limit exists and is finite and real, that's what it means to exist, then I would say that this integral exists and is equal to that value. In other words, the area under the curve from 1 to infinity between the curve and the x-axis is equal to whatever that limit value is. Now, if the limit does not exist, then I say that the integral diverges. All right, so that's a word that we're going to be using a lot this semester, especially when we get into sequences and series. So if the limit exists, we say it converges and the area under the curve is equal to that value. And if the limit does not exist, either it goes to infinity or it goes to negative infinity or it waffles around and doesn't settle down on any one number, then we say it diverges. And the area under that curve is not finite, right? So that's basically what we're going to do. This is our strategy. The integral itself must be evaluated completely with the limits of integration plugged in before you evaluate the limit. Okay, let's now move on and take a look at some more things that may come up while we're doing these. These types of limits very commonly will involve applications of L'Hopital's rule. Don't be surprised to see L'Hopital's rule creeping in here. After all, you're taking the limit of something, so don't be surprised. Limits, again, being the most powerful of the three constructs in calculus. You have the limit, the derivative, and the integral. My personal opinion is the limit is the most powerful because the derivative is defined to be the limit of the difference quotient. So you can't have a derivative if you don't have a limit. And when we're talking about the integral, there are two types, indefinite and definite. The indefinite is the antiderivative, but again, you don't have a derivative if you don't have a limit. And the definite integral is the limit of the Riemann sum. So again, if you don't have a limit, you can't have a definite integral. So really everything comes down to limits. Limits are so important. Keep in mind that these limits may exist and may not. And that may mean that there's a finite amount of space if the limit exists, or if the limit doesn't exist, then we either just can't say, or there's not a finite amount of space. Okay, now, what do we do if both limits of the integration are improper? This is something that we have not talked about yet, but we need to talk about this right here. Now, how would we handle this? Now, what do I mean by this? Let's suppose that I were looking at the integral of 1 over x squared again, but I were integrating from negative infinity to infinity. This is what I mean by both limits of integration are improper. They're both a direction and not a finite real number. Well, we have a problem here because the rule was to replace the limit of integration with a dummy variable, c, and then to take the limit as c approached that value. But that's only one limit, and I need to replace two things. But I can only take one limit at a time, which means that I can only replace one limit of integration at a time, which means that only one of these can be improper at a time. Well, that's going to be a bit of a problem for me. So if I can only have one that's improper at a time, and in fact, I'm not liking this one. Does anybody see why I'm not liking this example right here? This isn't just a type 1 who recognizes that it's also type 2. Yeah, if x is 0, this integrand is undefined, and 0 is between negative infinity to infinity. So let's just fix our example right here and make it x squared plus 1. So slightly different, but not a whole lot different. Now I don't have that problem. There's no value, real value, that will cause the denominator to be 0. So it's defined for all real numbers. And now the only problem I have to worry about is type 1, which is the limits of integration are improper. But again, if I'm going to do that, I can only replace one at a time. So what do I do? I've got 2 to replace. Then you're going to use one of the properties of the fundamental theorem of calculus, which says, if you want to integrate from 1 to 5, can't you integrate from 1 to 3 and then from 3 to 5? I mean, you don't have to go 1 straight to 5, do you? No, you don't. So in case you're wondering, if you want to integrate from 1 to 5 of x dx, you could also integrate from 1 to 3 of x dx plus the integral from 3 to 5 of x dx. Doesn't that accomplish exactly the same thing? Where the upper limit of the one on the left is 3 and the lower limit of the one on the right is 3. These numbers match. So go from 1 to 3 and then 3 to 5 instead of 1 to 5. We need to use a similar idea to simplify this right here so that only one of the limits of integration is improper at a time. So we just pick a convenient value that's in this interval between negative infinity and infinity. Now, any convenient value will do. You don't have to make it complicated. You can pick an easy one. My favorite, of course, is 0, provided 0 doesn't cause the denominator to be undefined. So in other words, I would write this as the integral from negative infinity to 0 of dx over x squared plus 1. plus the integral from 0 to infinity of dx over x squared plus 1, right? So could I have broken it at the number 1 instead of at 0? Yes, of course. How about 5? Go for it. 10? Yes. Pi? Yes, but why would you, right? You're making it more complicated. So you can break it at any convenient number that's between the original lower limit of integration and the original upper limit of integration. That gives me a constant, a known constant for one of the limits of integration in each integral. And then I only have to replace the one improper one. Now that will give me the sum of two integrals, and each one will become a limit with the improper limit of integration replaced with C or with D. And since these are different, I would use C for maybe the first one and D for maybe the second one. And then we're approaching as we come along. Now, here's an example of what I did just above. You can see that what I've done here is I've replaced or split it into two integrals connected at the 0, right? But you could just as easily have split it at 5 or 1 or any particular value that you want. Now, when we do this, when we split it, we're actually evaluating the limit from one side only. So this kind of affects the evaluation of the limit as well. This gives us a one-sided limit. So this becomes the integral, and we're going to have a limit, and we're going to let the first one be C approaching negative infinity, and we're going to have the integral from C to 0 of 1 over x squared plus 1. Now, C is approaching negative infinity coming from the right side, right? Because it's the lower limit of integration. So in essence, you're really approaching negative infinity from the right side. And remember, the way you indicate that is with a plus in the power position above that, right? And then the second one, of course, is we're going to have another limit over here, and I would use a D, not to be mistaken for C. And this is going to be the integral from 0 to C of 1 over x squared plus 1 dx. That's D, not C. And this is approaching infinity, but really from the left side, right? So we're coming at it from the left instead. I mean, it doesn't make sense to approach positive infinity to the right. Then you can't even do that, right? But in essence, if these were numbers, then we would have the one-sided limits. And this is kind of what you would have to evaluate in order to evaluate whether or not the area between this curve and the x-axis is finite, right? Now, let's go ahead and move on to an example. In this example, we are looking at the integrand 1 over x. This is our function, which is the basic rational function. You can see it here in blue. This is the graph of 1 over x. And we want to integrate from 1 to infinity. So we're really starting here at 1 and going out to the right. Now, the space that's under the curve is getting smaller. And I did go ahead and make a picture of that space for you right here. So you can see that the space is getting smaller as it goes out to the right, but that doesn't guarantee it's finite. It may not be getting small enough, fast enough. And we're going to see this idea coming back again when we talk about sequences and series. So the question is, does it get low enough, fast enough that that's a finite amount of area, even though it's in an infinite space? Now, clearly the curve is decreasing as x goes to infinity. I mean, the limit of 1 over x as x goes to infinity is 0. This curve is approaching the x-axis, but it never quite gets there. So what we want to know is there a finite amount of area? Can I go to Home Depot and buy a finite amount of paint that will completely paint that infinite region, even though I can never be done? Because, yeah, I know it kind of plays with your head a little bit. Okay, so let's go ahead and write down what our integral would be. So we have the integral from 1 to infinity of 1 over x dx. Now we know that we want to replace the infinity with a dummy variable, which I'm going to call c, and then I have 1 over x dx, and then I have to take the limit as c approaches the limit of integration that was improper, which is infinity. Now, when I'm looking at this particular one, remember that we have to completely and utterly finish the definite integral before we can start the limit. Don't mix the two. It leads to disastrous results. So we have the integral of 1 over x dx, which of course is the natural log of the absolute value of x. So this is going to give me the limit as c goes to infinity of the natural log of the absolute value of x evaluated from 1 to c. And again, we want to completely evaluate this definite integral by plugging in the limits of integration before we evaluate the limit. So in our next step, we're going to still have the limit on the outside, which is not taking place yet because I have not finished plugging in values. I have the natural log of the absolute value of c minus the natural log of the absolute value of 1. Now, the absolute value of 1 is 1, and the natural log of 1, you should know, is 0. So this part right here goes to 0. And that gives me the limit as c goes to infinity of the natural log of the absolute value of c. Now, I need to think a minute about this absolute value. Can I drop the absolute value? Well, c is going to infinity, so at some point it is strictly positive. So at that point, that means that I can drop the absolute value. Now I need to evaluate what this does, but to evaluate what this does, I need to think about what the graph of natural log looks like. So I'm going to come over here and I'm going to sketch out a graph of natural log. Remember, natural log is the slowest growing function that we have. It just takes freaking forever to get up to infinity. It is the slowest growing class of functions we have, but it does go to positive infinity as x goes to infinity, just very, very slowly. Well, what does this mean? As c goes to infinity, what is the natural log of c? I said it grows very slowly, but it does go to infinity. As c moves across, the natural log value does go to infinity just super, super slowly, which means that the value of the limit is infinity, which means, coming back up here, that this space we see here shaded in blue is not finite. It is in fact infinite. There is no amount of paint in the world that will cover that space. It is an infinite amount of space. So we would say that it diverges. Let's take a look now at the next example, which is example number 2. In example number 2, we're looking at the one that I actually wrote out towards the beginning of this discussion, which was the integral from 1 to infinity of 1 over x squared dx. Now, the graph of 1 over x squared, oh, and I messed up my graph earlier, didn't I? Sorry about that. I was thinking of something slightly different. So we've got 1 over x squared. Basic idea is the same. So you'll have to bear with me. So we have 1 over x squared here. And we're looking at this, it's undefined when x is 0, which means that we have this vertical asymptote here. These can cause problems when they're between the limits of integration. But this is at 0, and 0 is not between 1 and infinity, so I don't have to worry about that. I'm just focused on the right side, starting at 1 and going to infinity. So when I'm looking at this right side between 1 and infinity, I'm really looking at this region that I've got right here. Now, it does get very low very quickly because of the square. So when we're looking at this square right here, here is a graph of 2 different functions. So let me put on here what these functions are. In green, we have the graph of 1 over x. And in blue, we have the graph of 1 over x squared, which gets much lower, much faster. Now they both intersect at the point 1, 1, right, as you might expect. But 1 over x does not drop as low, as fast as 1 over x squared does. So this area, as we move off to the right, is diminishing faster than the area under 1 over x. Now, we just saw that the area under 1 over x was not finite, right? Is it possible that this area under 1 over x squared gets low enough, fast enough that it's a finite amount of area, even though it's an infinite region? Let's take a look. So we're going to be integrating from 1 to infinity of 1 over x squared dx. In order to integrate this, we need to replace the infinity with a c, and then we need to take the limit as c approaches infinity. Now, 1 over x squared, I'm going to write as x to the negative 2 dx, so that I can basically use the power rule for integration. Remember, I've got to complete the definite integral before I can even start the limit. So this is going to give me a limit, c approaching infinity on the outside, and I need to complete that definite integral. So an antiderivative here, applying the power rule, add 1 to it, gives you x to the negative 1 divided by negative 1. So I have x to the negative 1 divided by negative 1, and that has to be evaluated between 1 and c. Now, one of the tricks that I like to use whenever I can is that if I have a negative in the antiderivative, then I can eliminate the negative by switching the order of the limits of integration. So I'm going to take care of that negative by switching the limits of the order of integration. And this would give me 1 over x now to the first power, and instead of between 1 and c, between c and 1. And that's equivalent to what we had before. It just reduces the number of negatives I've got running around and makes it less likely I'm going to mess up. Now, another good option that you can do to deal with these negatives, because the negative 1 doesn't depend on c, you could actually factor it out of the limit and it would be okay. All right, it can be factored out of the integral and it can be factored out of the limit, and that would be fine. I prefer to deal with it this way. So now I'm going to plug in the limits of integration. I've got to complete the definite integral before I can take the limit. So I have the limit as c approaches infinity of the value of 1 over 1, started to write x again, minus 1 over c. Okay, well, 1 over 1 is just a constant 1. And now what I have is the limit of a difference, right? So I've got the limit of a difference. And remember that limits are the most powerful of the three constructs. We can do almost anything with a limit. You can even split products and quotients, which you definitely better not do with derivatives and integration. But you can with a limit. So I can split the limit, and I can take the limit as c approaches infinity of 1 minus the limit as c approaches infinity of 1 over c. So when I'm looking at this particular one, the limit of a constant is the constant. So this just gives me 1. And the second one, as c goes to infinity, the denominator blows up. That's our technical term, blows up, goes to infinity, and 1 over infinity drives down to 0. So this one goes to 0. Hopefully you remember your calculus 1. And we get 1 minus 0, which is 1. In other words, the amount of area under that curve from 1 to infinity is precisely 1 square unit. Blows the mind, doesn't it? Let's take a picture at what this looks like. So here's our graph again. So this curve in green is the graph of 1 over x, whose area from 1 to infinity is not finite. And this is the graph of 1 over x squared. And then what do we have here in this sort of red color? Well, this is 1 square unit of area. It goes from 0 to 1 on x and 0 to 1 on y. So this is 1 square unit. This amount of paint is exactly the amount of paint I need to paint the blue region. In other words, the red area and the blue area are equal, not approximate. They're equal, precisely the same, which is a really startling idea. So now we've seen how we can use the limit as C approaches an improper limit of integration to evaluate an improper integral of type 1. Let's take a look at one more example. Earlier, I must have been thinking of 1 over x squared plus 1 instead of 1 over x squared. So when we're looking at this one right here, we've got this example 3, and we've got this graph that's going on right here. So this is the graph of 1 over x squared plus 4. And notice that this one is going from negative infinity to infinity. So the region we want to find out about is really that entire region between the curve and the x-axis. So it's the entire thing. So when we're looking at it, it would be this region right here, which is shaded in blue. And the question is that finite or is it infinite? I don't know. I don't know what it is. It does look like it's getting low pretty fast. I mean, certainly if I cut it off between -1 and 1, the area in between is finite. And if that's finite, makes sense that might be finite. Would they add up to a finite? Weird things happen with infinity, so it's not entirely clear what would happen. So we're going to have to evaluate this by splitting it apart at some value between negative infinity and infinity. You can split it anywhere, but again, it does make sense to go ahead and split it at something easy to compute, 0 being the easiest thing of all to compute, and 1 being the second easiest. So we're going to split this one up at 0. So I'm going to start with the original integral from negative infinity to infinity of 1 over x squared plus 4 dx. And I'm going to split it from negative infinity to 0 of dx over x squared plus 4, plus the integral from 0 to infinity. I can only have one limit of integration be improper at a time because I can only evaluate one limit at a time. So I have to have a constant as one of the limits of integration. And the way to do that is just split it at some number between the lower and upper limits of integration. Now, how am I going to evaluate this? Well, I need to replace the improper limit of integration with a dummy variable and take the limit as it approaches that value. So now I'm going to split it. So I have the limit as c approaches negative infinity of the integral from c to 0 of dx over x squared plus 4 plus the limit as d goes to positive infinity of the integral from 0 to d of dx over x squared plus 4. Now, I said that the methods of improper integrals is not exactly an integration technique because we're not looking at patterns of the integrand. We're instead looking really at either the limits of integration or at a value that causes the integrand to be undefined. So when we're looking at this right here, we'll need to go back to the known techniques of integration that we've covered: integration by parts, trig integrals, trig substitution, partial fraction decomposition, worst case, grab an integral table or a computer algebra system in order to integrate this right here. So how do you integrate it? All right, I hope that you remember that this is a trig substitution problem. This looks like a something squared plus something squared with a plus, so it's got to be tangent. So I'm going to pause the video, and I want you to pause it as well. Work out what the integral itself would be. They're identical, right, on the inside. The only difference is going to be what you're substituting in as the limits of integration. So let's work out the integral and then restart the video to compare and make sure that you solve that part correctly. Let's see how far you got. So we had split it into two separate integrals, and then we replaced the improper limits of integration with our dummy variables and took the limit as the dummy variable approached that improper limit. When evaluating the integrand itself and deciding how to integrate, it reminds us of the Pythagorean theorem. And because they're both positive terms, it's got to be the one with tangent, reminding us of tangent squared theta plus 1. It's basically the form u squared plus a squared, which means that we can then have our value of u squared being x squared, and our value of a squared being 4, so a is 2. Now, our substitution factor for the particular type of trig substitution is u equals a tangent of theta. So u is x, so we have x equal a, which is 2 tangent of theta. This is our primary substitution equation. Now we need to go ahead and rebuild the parts of the integrand so that we can replace it from an integral in terms of x with a differential dx into an integral in terms of theta with a differential of d theta. So we have to replace the dx and replace the x squared plus 4. Now keep in mind, however, that the c and the 0 are x values. So we're going to be going back to those, but as x values, not as theta values. And I'll show you how I notate that in below. I left it off on purpose so that I could show you as I go through. So the first thing we do is rebuild the denominator, x squared plus 4. X is 2 tangent of theta. So we have 2 tangent of theta quantity squared, which gives us 4 tangent squared theta plus the 4, which was next to it. Factor out the common factor 4, gives you tangent squared theta plus 1, which is secant squared. This then reduces it from 2 terms to 1 term and switches it from being in terms of x to being in terms of theta. We go back to our original substitution equation and we take the derivative with respect to theta of both sides so that we can solve for dx in terms of theta and d theta. Then we go back to the integral and we replace these pieces. Now I said that you need to keep in mind that the actual limits of integration are x values. So to make sure that you remember that, what you should be writing here is x equals c and x equals 0 on each one of these to remind you that you cannot replace theta with those values. These are x values only. So x equals 0 and x equals d. Now what we have when we substitute the pieces in, 2 secant squared theta d theta replaces the differential dx, and the denominator is replaced by 4 secant squared theta. The 2 fourths gives us a factor of 1/2 on both. The secant squares cancel and we get the integral of d theta. Now when we integrate d theta with when integrate d theta, we get theta. Now remember that these limits of integration are x values. So this is x equals 0 and x equals d. So you cannot plug in these values into theta. They're x values, not theta values. So we've got to get out of theta and get back to x. And we again use our substitution equation. U equals a tangent theta, or x equals 2 tangent theta. We solve for the trig function, and that gives us tangent theta is x over 2, which means that theta is the arctangent of x over 2. Now we replace theta with the arctangent of x over 2. We can drop the x equals c and x equals 0 because these are now, of course, back to being a value depending on x. So this depends on x and these are x values as well. So we can drop them. We don't have to write it, but of course you can if you want to, if you prefer it. Now let's talk for a minute about this 1/2. This 1/2 is a constant, which is not going to affect the value when we evaluate this antiderivative at the limits of integration. It's a constant, which in fact could be factored out of that. And because it doesn't depend on c, it can also be factored out of the limit. So I could actually have the 1/2 at the front, then the limit as c goes to negative infinity, and then I can evaluate the arctangent of x over 2 between 0 or between c and 0. So I'm going to go ahead and evaluate that now by writing it out a little bit. So I have arctangent of the upper limit of integration minus arctangent of the lower limit of integration. Then I have the second one, and again, I'm going to factor the 1/2 out. Then I have the limit as d goes to infinity, and I can tell I'm running out of room. And then I'm going to have the arctangent, and I lost my over 2 here. This should be c over 2. All right, 0 over 2 is still 0, so that one is fine. And then coming over here, I should have d over 2 minus the arctangent of 0 again. All right, so now I've got these two different limits to evaluate, but first I need to complete the definite integral. I need to evaluate what they are. The angle whose tangent gives you 0, remember arctangent is defined between negative pi over 2 up to pi over 2. So quadrants 4 backwards and 1 forwards. So on the right half of the unit circle. So the angle whose tangent gives you 0 is 0. So this first one is going to simplify and become a 0. So this becomes 0. So now we have equals 1/2, the limit, c is approaching infinity, negative infinity rather, and this is going to give me 0 for the first one, minus, and then I have the arctangent of c over 2. Now I can't evaluate that because I don't have a real number to substitute for c. I'm instead going to be taking the limit as c goes to negative infinity. So now I want to go ahead and focus on the second one over here, and I want to plug in what I've got over there on that side. So I've got the 1/2 factor at the front. I have not evaluated the limit yet because I have not finished substituting my limits of integration in. Arctangent of d over 2 cannot be simplified yet because I don't have a value for d. And the angle whose tangent is 0 is again 0. So that term drops out. Now the 1/2 is a factor on both terms, so I can pull the 1/2 out of the whole thing, but we'll just leave it where it is. And we can evaluate what's left here. Now, when I'm looking at what's left here, I need to think about the functions for arctangent and what it looks like. So when I'm thinking about the functions for arctangent and I'm trying to evaluate it, I need to think about what arctangent itself looks like so that I can evaluate what the value of it is. So let's draw a picture of arctangent. Okay, so we want to draw a picture of arctangent, but before we do that real fast, let's do one more thing to simplify what we have to evaluate. We've got this negative here being multiplied by the arctangent of c over 2. The negative is just a -1. It's a constant factor. It doesn't depend on c, so I can factor it out as well. So because this term is negative and this term is positive, you could reorder them so that they're in positive minus a negative, but you can also leave it the way it is with just a -1/2 at the front. And then we have the limit as c approaches negative infinity of the arctangent of c over 2. And we'll need the graph in order to figure out what that comes out to be. And then we still have 1/2 the limit as d goes to positive infinity of the arctangent of d over 2. Now let's remind ourselves of what arctangent looks like. And what I've done is I've graphed it for you on Desmos, which is an online graphing calculator system. And so you can see here in black that this is the graph of arctangent from negative infinity to infinity. You can see the command up here in the upper left. And then there are two asymptotes on this graph. As it goes out towards positive infinity, it approaches the horizontal line y equal pi over 2, which you'll see right here in the second line down. And as it goes towards negative infinity, it approaches the horizontal asymptote y equal negative pi over 2. So we have this graph right here. So now let's go back to our equation and remind ourselves what we want to evaluate. So we can ignore the negative 1/2 for a minute and just focus on this part right here. We want the limit as c approaches negative infinity of the arctangent of c over 2. Now, c over 2, if c is going to negative infinity, becomes negative infinity over 2, which is really negative infinity. So the arctangent is approaching negative infinity. The x value is going towards negative infinity. What then is the y value of that going to approach? Well, as we come out this way, as x goes to negative infinity, the y value approaches negative pi over 2. And so now we can replace what we have there with a negative pi over 2. We've evaluated the limit using the graph. So we have negative 1/2 times negative pi over 2. Now let's take a look at the second one, the limit as d goes to infinity of arctangent of d over 2. So infinity over 2, again, it's still approaching infinity, just half as fast, but still approaching infinity. And when we look at the graph, as x goes off to the right, the y value approaches pi over 2. So for the second part, we have plus 1/2 of pi over 2. Now what we have, of course, is just a simple expression that we can evaluate arithmetically. We have a double negative, so it becomes positive, and we have pi over 4 plus pi over 4, which is pi over 2. Now you may think, oh my gosh, what does this mean? Well, this means that that is a finite amount of area, and it is equal to precisely pi over 2 square units. So let's go back to where we started a long time ago, which was this area right here, the area under the curve between 1 over x squared plus 4 and the x-axis. And we have found that, in fact, it is a finite amount of space. It's precisely pi over 2 square units. So from 0 to pi over 2 and 0 to pi over 2. All right, so hopefully this makes sense to you now, and you're understanding better how to deal with these improper limits of integration of infinity and negative infinity. Let's make note of one thing before we proceed any further. For students who are in my particular class, there's an error in the textbook. So note that this is here. This is for the OpenStax textbook, volume 2. I believe the page number is 334. Should be pi over 4, not pi over 2. So be careful about that. Now let's take a look at the type 2 integrals that are improper. So these are the ones that are harder to detect because they come about from an infinite discontinuity between the lower and upper limits of integration. In other words, a vertical asymptote in the graph between the lower and upper limits of integration. Now, they're easy to identify if you graph the integrand function because you'll see the vertical asymptote in the graph. But if you don't graph the integrand, it's very easy to miss these and to proceed as if it does not exist, and then you'll come up with the wrong solution. So when we're looking at these, what's basically happening is we've got a value between the limits of integration that causes the denominator of the integrand to be 0, undefined. Now, these are the sneakiest ones because there's absolutely nothing in the integrand or the limits of integration to warn you it's not proper if you're not paying attention. And there's nothing to stop you from integrating it and plugging in the limits of integration without taking that infinite discontinuity into account. There's nothing to stop you doing that. And there will be nothing in the wrong answer that you get to let you know it's wrong. In other words, there's no red flag that comes up that lets you know that you're doing something that's incorrect. So here are some ways to know for sure that it's improper. Two things. The easiest, of course, is to graph the integrand and look between the lower and upper limits of integration, the area, the interval over which you're integrating, and see if there's a vertical asymptote. If there's a vertical asymptote, it's improper, and we're going to have to deal with that. The other thing you can do is look at the integrand and ask yourself what would cause the denominator to be 0. Now, the example we just did, 1 over x squared plus 4, there is no value that causes it to be undefined. And so there can't possibly be a type 2 improper integral with that integrand. But yours may be something different, 1 over x minus 4, and then you would have a problem if x were 4. So you notice that there's a value that causes the denominator to be 0, and it's between the limits of integration. Then we have a problem. Now, how are we going to deal with this type of improper integral? We're going to do something similar to what we did when both the limits of integration were improper, both negative infinity and positive infinity, and that we're going to split the integral into pieces. But this time, what we're going to split it at is at that vertical asymptote, at that point of discontinuity. So we're actually going to split the integral into the sum of 2 integrals or more. You could have multiple places, but you've got to have a finite number of them. You can't have infinitely many places where the denominator is undefined. There must be finitely many of such points. So we'll split it apart at each point of discontinuity, and then we'll integrate each individual piece by evaluating one-sided limits. So let's say the integrand is undefined at x equals 4. So we could just simply be taking something like the integral of 1 over x minus 4 dx, and we could be integrating from 1 to 5. Now, again, looking at 1 over x minus 4 dx as an indefinite integral, there's nothing to stop you from integrating that. It'd be 1 over u du, natural log of the absolute value of u, and then you'd be going and plugging in numbers, and you'd be getting the wrong answer. Because between 1 and 5, we have x equal 4, and 4 causes the denominator to be undefined. There's a vertical asymptote at x equal 4. So we need to split this into 2 different integrals, and we're going to split it at 4. So we're going to take this apart right at 4, and we're going to integrate from 1 to 4 of dx over x minus 4, plus the integral from 4 to 5 of dx over x minus 4. Now, again, the 4 is what's causing a problem for us. So we're going to take that 4 and we're going to replace it with a dummy variable. It's not infinity or negative infinity, but it is a vertical asymptote, right? It's causing 0 in the denominator. You got to get it out of there. So we're going to replace it with c or d, and then we're going to take the limit as c approaches that 4 from one side or the other, right? So let's take a look at what that might look like right here. So in this first integral, what I'm going to do is I'm going to replace it with a c. So I have the integral as c approaches 4, and I have the integral from 1 to c of dx over x minus 4. Now, it's not just approaching 4, it's approaching 4 from the left, right? Because it's starting at 1 and going towards 4, so it's approaching 4 from the left. So this is actually a one-sided limit. C is approaching 4 from the left, and we use a negative in the power position to show that. Now, what about this other integral that we have here? I want to use a different dummy variable. Again, you can name it anything you want, or you can use a symbol like happy face. And I'm going to allow this one to be d. So I have the limit as d approaches 4 from one side or the other. I haven't figured that out yet. And then I have the integral from d to 5 of dx over x minus 4. Now, which side is it approaching 4 from? Well, it's going from 4 to 5. So it's the numbers to the right of 4, not to the left. So that must mean that I'm going to be approaching 4 from the right-hand side or from above. And so I get a one-sided limit there. And this is how we have to deal with this. Now, again, there's nothing in this integrand or limits of integration to throw up a flag and say, whoa, you better split this apart at 4 and replace the 4 with dummy variables and evaluate one-sided limits of the definite integral. There's nothing to throw that up. You have to be aware that it's an issue and be looking for it. Now, what if both the limits of integration are also something that is improper? Well, then you're going to have to split it multiple times, right? You'll have to split it at the improper integral, and you got to split it at a random number. So you're going to have to split it so that each time you evaluate that integral, only one of the limits of integration is that improper thing, where the improper thing is either infinity, negative infinity, or the x value of a vertical asymptote. Those 3 things are improper. And anytime you split the integral, you can only have at most one improper limit of integration. One that's infinity, one that's negative infinity, or one that is the x value where a vertical asymptote exists. Otherwise, you're going to have to break it into more convenient places. And that may mean that you, instead of integrating once or twice, that you're actually integrating 3 or 4 different integrals and adding them together. After you've completed the definite integral and substituted the limits of integration, then you take the limit of each piece. Now, for the ones that are approaching the vertical asymptote improper limits of integration, it'll be a one-sided limit. Make sure that you complete the integration and the substitution of the limits of integration before you evaluate that limit. Let's now take a look at this example right here, which is example number 4. And in example number 4, our integrand is 1 over x minus 2, and we're integrating from 1 to 4. Now, again, there's nothing in the integrand to warn you not to just do 1 over u du and then substitute in the limits of integration. There's nothing in there that's going to be a red flag necessarily. But it is a red flag because this is undefined at 2, and 2 is between 1 and 4. So when we're looking at this graph, this is a rational function. It's been shifted to the right by 2. And so it has this vertical asymptote here at x equal 2. And we're talking about the area between the curve and the x-axis from 1 to 4, which is these 2 blue regions added together. So between 1 and the vertical asymptote at 2, it's actually below the axis. And between the vertical asymptote at 2 and 4, it's actually above the axis. So we have some positive area and some negative area. But the question is that a finite amount of space or is it infinite? Because again, this vertical asymptote creates an infinite amount of space as it goes up forever and ever. And that's our question. So now what we want to do is we want to split it apart. So we're starting with the integral from 1 to 4 of dx over x minus 2. And we know that it is undefined at 2. So we need to split it. So we're going to integrate from 1 to 2, and then from 2 to 4. Now, in order to do this, we're going to go ahead and replace the improper limit of integration, which corresponds to a value that makes the denominator 0. We're going to replace that with a dummy variable. And I'm going to use 2 different dummy variables in this case, like I did the last time. And I'm going to have the limit as c approaches 2 from below c, from values between 1 and 2, of the integral from 1 to c of dx over x minus 2, plus the limit as d approaches 2 from above, numbers to the right of 2, between 2 and 4, of the integral from d to 4 of dx over x minus 2. Now this one is far simpler to integrate because it just has the form of 1 over u du. So we can write that down and then we can go ahead and do the integration. U equals x minus 2. So du equals dx. And so we end up with the integral of 1 over u du, which is the natural log of the absolute value of u. And then going back to our original, that would be the natural log of the absolute value of x minus 2. So when we're coming back to that original, and we can put it back into our two integrals and limits, we have the limit as c approaches 2 from below or the left of, now we've evaluated, so I'm going to open big brackets. So I have the natural log of x minus 2 in absolute value between 1 and c. And then the second one becomes the limit as d approaches 2 from the right. And again, the same antiderivative, natural log of absolute value x minus 2, but this one evaluated between d and 4. All right, so now we've reached this point. We still can't do the limit. We have to finish the integral by plugging in the limits of integration. So I'm going to plug in the limits of integration and let's see what we come up with. So you may want to pause the video, work it out, and then turn the video back on and see if your answer matches mine. So let's compare our processes and see if we came up with the same thing. So I evaluated the integrals by plugging in the limits of integration, which gave me natural log of c minus 2 in absolute value, minus the natural log of, in absolute values, 1 minus 2. Now, 1 minus 2 is a negative 1, but it is in those absolute values, which are so critical, don't leave them off, of the integral of 1 over u du. And that gives us the natural log of 1, which is 0. So this term right here drops out, and I'm left with this particular limit on the front. Now, the second one, when I substitute the limits of integration, I get the natural log of the absolute value of 4 minus 2, minus the natural log of the absolute value of d minus 2. Now, the second part I can't do yet. That's where I need the limit. But this first part, the 4 minus 2 is just 2, and the absolute value of 2 is 2. So that gives me the natural log of 2. Now, when I scroll down a little bit more, I can take it a little bit further. I still need to evaluate this limit here in blue. And on the right, for the two that are in black, the limit of a constant is the constant. So I get natural log of 2 as a constant. And then I can pull the negative outside of the limits. It does not depend on d, and evaluate the limit as d approaches 2 from above of the natural log of the absolute value of d minus 2. Now, these absolute values are pretty important here. They're going to be very critical. Now, let's see what happens right here. And let's go ahead and throw the graph of natural log up onto the screen right here so we can be thinking about what natural log does. Remember, it is the slowest growing function. It does eventually get to infinity as x goes to infinity. And as x gets close to 0, it goes down to negative infinity. So remember, it's only defined over there on the right half of the real plane. So when we're looking at the first limit in blue, c is approaching 2 from numbers below 2. So like 1.9, 1.99, so forth. But they're getting close to 2. So at some point, it's going to be practically 2, but that would make this 0. So in other words, because the absolute value, the numbers become positive, and that means that they're very, very small and getting close to 0. Well, what happens when this is approaching 0? Well, when natural log is approaching 0, it's going towards negative infinity. So this first one here in blue is equal to negative infinity. And then we have plus the natural log of 2 from the middle one. And now we need to evaluate this third one over here, this limit that we've got right here. D is approaching 2 from above. So from numbers like 2.1, 2.001, 0001. And so it's getting, again, very, very close to 0. The numbers are positive, but it wouldn't have mattered because it's inside an absolute value. So again, it's getting close to 0. And as natural log approaches the natural log of 0, the y value goes to negative infinity. but we've got a negative on the outside. So we have a minus negative infinity. Now, minus a negative infinity is going to give us a plus sign. So this is going to give us negative infinity plus the natural log of 2 plus infinity. Now, here is where some students really, really struggle with interpreting this result. The problem isn't with the natural log of 2, it's finite. The problem is that we have two competing directions. This wants to pull it to negative infinity, this wants to pull it to infinity. You cannot say that they cancel out. Remember that there are different sizes of infinity called cardinality. So there are different sizes of infinity. And if this is stronger than that one, it'll pull it towards positive infinity. But if this one is stronger than that one, it'll pull it to negative infinity. But if they're roughly the same size, they could cancel each other out and stop at any finite real number, which means there's no unique answer here. I can't say what the result is going to be. And remember that infinity minus infinity is an indeterminate form. So when we see this infinity minus infinity, it's indeterminate, but I've already done the limit. So I can't apply L'Hopital's rule. There's nothing more to be done here. This is the result of the limit, and it is inconclusive. So I would have to say it diverges. In other words, the area under that curve is not finite, at least not so far as I can predict. This is just an inconclusive result. I would say it diverges, right? Because I can't predict. I don't know. It's the different possibilities here. So we would say not finite because we cannot predict. All right, let's take a look at our last example, which is number 5. And on this one, we have the definite integral from -5 to 8 of 1 over x squared minus 4 dx. So when we work through this one, this is, again, a rational function. And so you can see it graphed here in green. It's got two vertical asymptotes at -2 and 2. And so we look again at the denominator to see what makes it 0. We got -2 and 2. And we note that both -2 and 2 fall between the limits of integration. And that means that we will need to split this into multiple integrals. So we're going to have to integrate from -5 to -2. And then we're going to have to integrate between, well, now I've got a problem because my first instinct would say, well, go to the next one that doesn't work, which was 2, but I can't do that because I can only have one improper limit of integration at a time. And so I need to split it somewhere else between -2 and 2. And an obvious place to do that would be 0 or 1, something between -2 and 2. So I'm going to go between -2 and 0 of dx over x squared minus 4. And then I'm going to have to integrate from 0 to 2 of dx over x squared minus 4. And then I can finally go from 2 to 8 of dx over x squared minus 4. Now, again, why did I have to split it at 0? Now, it didn't have to be 0. It could have been a couple of different things. But the basic rule is only one of the limits of integration at a time can be an improper thing. An improper thing is either positive infinity, negative infinity, which we don't have here, or the location of a vertical asymptote, which we do have. So that means that this one right here is improper, this is improper, this is improper, and this is improper. In each individual integral, only one limit of integration at a time can be improper. I couldn't go from -2 to 2 because then they'd both be improper. So I've got to split it at some convenient place between them, 0 being the easiest one to split it. So go ahead and pause the video, work out this particular value, and then restart the video to compare your answer to mine. So how'd you do? Did you give up? I wouldn't blame you if you did. This is probably one of the worst possible problems. It's just an absolute nightmare. So why did I pick it? Because I figure if you can follow the process on one of the most difficult problems possible, then you can certainly do it on the easier ones, which you will find on the homework. So we had taken this and we'd split it up, making sure that only one limit of integration at a time was improper. And then I'm going to write them as limits. Now I chose C, D, F, and G. I don't like to use E because E to me is Euler's number. So I have the limits of these definite integrals as I'm going across. Now, all of the integrands are dx over x squared minus 4. So I decided to go ahead and find the indefinite integral of dx over x squared minus 4 first. And then I could just take the result, antiderivative, and evaluate it at the limits of integration of each one. Now that turned out to be an enormously complicated process. So let's take a look at briefly. I'm not going to go into great detail, but briefly, this is what you need to do. It is Pythagorean in nature. It is something squared minus something squared. It's reminiscent of secant squared minus theta minus 1, and so it's u squared minus a squared. We make the substitution u equals a secant of theta. We rebuild the denominator, we find the differential dx, and then we substitute these values into the integral. That leads us to the integral of 2 secant theta tangent theta d theta over 4 tangent squared, which reduces to 1/2 the integral of secant theta over tangent theta. Now, this isn't one of the ones that I know off the top of my head, so I instead converted everything to sine and cosine and went ahead and simplified it, and it turned out to just be cosecant of theta. So that was a trig substitution process that I'm engaged in here. And then I got this integral of cosecant of theta, which happens to be, yeah, you got it, a trig integral. So then I applied this technique here of multiplying by a form of 1 of cosecant theta plus cotangent theta. And notice that in the derivative, you get double negative here. And so the negative can be factored out. And so you basically end up with negative 1/2 the natural log of the absolute value of cosecant theta plus cotangent of theta plus a constant if it were an indefinite integral. Now mine's actually definite integrals, but at that point, the answer is in terms of theta, and I've got to get back to x. So I use my substitution equation again, x equals 2 secant theta and the right triangle trigonometry. And that lets me rewrite this result down here. And in fact, I could go ahead and write it in a slightly more combined format. Since I have a common denominator, I could write it as x plus 2 divided by the square root of x squared minus 4. And then, of course, plus the constant of integration. So this is the one that I want to use as the antiderivative of this integral, and then I want to plug in the limits of integration. So all I've done here is I've taken this negative 1/2 constant and pulled it out. It's not going to affect the value when I plug in the limits of integration, and it doesn't depend on any of the dummy variables, so I can pull it out of all of the limits, which means I can pull it to the very front. So here's my negative 1/2 outside the gray brackets. And then I need to evaluate each of these at the different limits of integration. So I've got the same antiderivative in all 4 places with the different limits of integration. So you can see the process going on here. Now, next step, let's focus on just this bottom part right here. And you can already see the answer coming up, and you may go, whoa, how did you go from there to there so fast? Okay, well, I didn't go from there to there so fast. The first time I worked this problem, I worked it out completely, and it took me an enormously long amount of time. And then I got down towards the end and realized it had to diverge because there were some values that didn't make sense here and wouldn't have made sense even if I'd split it at something other than 0. So the problem is this splitting it here that we did at the different limits of integration. And I think I've got the wrong values right here. That's supposed to be the integral from g to 8. How did that end up off? So let's go ahead and fix that before I make any other mistake. So this should be from g to 8. So checking through, they all look good now. Okay, so what's the problem and why can I just write diverges without having to actually plug them in and then evaluate the limits? Well, if I were to plug in the c and the -5, I can see that this is not going to be a problem here, plugging it in, because c plus 2, it's fine. C squared minus 4, that's fine. -5 squared is 25 minus 4, which is 19, so that's all good. And even though I have -5 plus 2, which is -3, it's an absolute value, so that's not a problem. This next one is a problem. When I try to substitute in the upper limit of integration 0, I get 0 squared minus 4 under a square root. Well, that's not real. It exists, it's just imaginary, but it's not real, and I'm looking for a real solution. And you may say, well, yeah, well, just don't split it at 0 then, split it at 1. Well, it won't matter. I had to split it at a number between -2 and 2, and no matter what value I pick between -2 and 2, what results under this radical is going to be a negative. And that means that this is not a real value. And since the value of the definite integral is not real, the limit of it is not real, and then I know it diverges and I can stop right there. So it would also have been a problem coming down here on this one as well. So this one and this one are going to be a problem no matter where I break it between -2 and 2. So sometimes it does help to kind of take an overview picture or a big picture look and kind of imagine, am I going to run into any problems when I start plugging in these values? And you'll notice I used a lot of color coding here to help me keep track of where I was, because it's very easy on these problems to lose track of where you are and lose pieces of information that you need. So I highly recommend using highlighters, different colors, circle things, box things, highlight them, help yourself to make sense of the pieces of information that you have. So this is the end of this particular video. I hope that you have enjoyed this particular chapter on techniques of integration. We'll be taking a look at some differential equations next in chapter 4, just the basics of differential equations, since there are actually 2 entire courses on differential equations in the undergraduate curriculum. And we're just going to take a very, very high level basic look at what some of the definitions and the basic processes of solving a differential equation are. I hope you'll join me in the next video.